I'd say that's good enough. Oh my goodness. Give me 2 seconds to just grab my tea. I'll be right back. Testing, testing, 1, 2, 3. Hello, hello, hello. Yeah, I think that's good. Good. My goodness. Yeah, 1JC3. For those of you who don't know, that's the Haskell course that all the CompSci people are taking at the same time as they're taking this. So you CompSci guys, you're having the delectable fun of having to pick up on 2 different types of programming at the same time in very, very different paradigms. Yeah, this is jasmine green tea, which is one of my favorites for the morning while my coffee is still having caffeine in my system. It's a nice lighter caffeine variety of tea. Anyway, yes, 1JC3 is yeah, Monk's Blend is good. I don't know, it's okay. Yeah. So I don't know if they've recommended this textbook to you guys in 1JC3, but yeah. There's a textbook which I found to be the best textbook on how to learn Haskell. If it hasn't been recommended to you, have they recommended the book Learn You a Haskell for Great Good? Because if they haven't, then they should. It's Learn You a Haskell for Great Good. There we go. The whole thing is actually available online for free, so you don't even have to necessarily order the book. Sorry for all of the people who are not CompSci students. We'll get to the lecture in good time. So this is the book. You can read it online for free, and it is, I believe, a very, very good introduction. This is the book that I learned Haskell on, and it is, I think, a very good resource. It goes through things sort of very it's a very well-structured curriculum, and it doesn't necessarily assume that you're good in other programming languages either. It just assumes you know some math. So, oh good, you guys are using it? You have... Okay. Yeah. The craft of functional programming. Well, let's put it this way. If I were putting together the Haskell course from scratch, I would... if I were putting together the Haskell course from scratch, I would use Learn You a Haskell for Great Good as the course textbook. HTML is decidedly worse than Haskell. Haskell is beautiful. Haskell is the programming language that everybody else is trying to use. Anyway, so when you have a course like this, sometimes the thing that you have to do is you have to go out and get some external resource, bring that into your knowledge, in order to, study up on stuff. But I would recommend, as a study, as a thing to go through, Learn You a Haskell for Great Good is a great one. Anyway, yeah. Anyway, yeah, Haskell is a beautiful language. It is, in terms of its semantic elegance, it's my favorite language. Yeah, so, anyway, we should probably actually do the lecture for today. Sorry, this is technically a comp sci course, so I do feel a certain obligation towards all my comp sci students to make sure they're not suffering too much with their degree programs that they have selected. But yeah, anyway, so let me just look up our lecture slides for today. Sorry guys, I'm a little bit behind today. I've been having to deal with some, shall we say, unusual problems in the other course, which has required a lot of my time over the last couple of days. Open it with events. There we go. Thank you. It's always nice when they do what you tell them to. So, let me just check to see if there's anything interesting going on in the chat. Boom, boom. Well, the thing about Learn You a Haskell is that it has cartoons, so it's just more fun. And I feel they explain things really well in that book. So I find a lot of the programming, programming textbooks kind of exist in one of two camps. They either assume you know every other programming language, or they assume you know nothing. And if you actually know nothing, it's better to go with one that assumes you know nothing. But anyway, it's got an elephant on the front. How can you not like that? And incidentally, when I say read the textbook, probably you only have to do the first 3 chapters or so, and go through the exercises in the first 3 chapters. And when I say exercises, that book is structured as here's a thing to do, here's some code that does it. There's no questions at the end of the chapter or anything. It's like one long tutorial. But if you do the first 3 chapters of it, you should have enough of a basic understanding of Haskell to be able to plug other things that you're seeing into that framework. But, that's also ostensibly the purpose of the course itself, so I probably shouldn't step on other professors' toes too much. Anyway, so we were talking about statements, a thing that Haskell doesn't have. We had done all this, factorial, yep, we had done that. While loops. We had talked about factorial 2, 3, and 4. Yup. I do not think that we had done factorial 5. Yeah, I remember doing this slide, because the previous examples, we were all starting I at 0 and counting up to n. But in factorial 4, we're starting at n and counting down to I is greater than or equal to 1. Sorry, to, we're counting down while I is greater than or equal to 1. So just to recap what we're talking about here with factorial, the factorial is an operation that tells you the number of unique permutations. It's a combinatorial thing. And we were doing some basic implementations of it in Python using loops. Later on, we're going to see how you can do this in recursion as well. Recursion being the thing that Haskell uses. Doop, boop, ba-doop, boop. Checking chat. Oh, so the problem with getting the star in there, what that typically means is that you have an infinite loop. So there's something wrong with your code such that the code is never terminating. So you need to kind of examine your code, see if, you know, you're not incrementing the index or doing something that prevents that code from terminating. That's why you're getting the star in brackets on Jupyter. You don't like online school? I really miss having a chalkboard. Anyway. Well, you know, there's an old statement that's not quite, you know, Hoyle anymore, but Linux is the brotherhood of datelessness. That's what they used to say about Linux. But anyway, so factorial. Yes, yes, yes. So it is also possible, rather than declaring I separately, we may also modify the function parameter directly. N here is the function parameter. This is what's known as the formal parameter, and this is the actual parameter. So you will also sometimes hear me call these arguments. Argument is a term that's used for these in a programming language like C. So this is your formal parameter. This is your actual parameter. The way that Python works with respect to these is when you put something into a function call, i.e., when you create a formal parameter, there is implicit assignment that's going on. So it's like the statement n becomes x is inserted immediately after the function definition here, or between here and there. So because that's the case, it is correct to think of n as a new variable that may be assigned a value without affecting the value of x outside of the function. This is kind of an important thing. It gets more important once we start talking about functions a little bit later on. But that's known as the pass-by assignment semantic. So we can modify n however we like inside of the context of the function, and any modifications that occur will stay inside of that function. They are scoped locally to the function. So if we ask what x is, well, actually, we can just do this. Let's, oh my goodness. Python 3. I was trying to get a good paint program for Linux that's harder than it seems, but it was Krita that I ended up going with. Anyway, define factorial, we'll just abbreviate n. F is equal to 1, while n is greater than or equal to 1. F equals f times n. N equals n minus 1. Return f. Factorial. So if we assign x some variable x the value of 5, x is 5. If we call factorial on 5, the result will be the factorial of 5. And if we ask what the value of x is again, notice that x is still 5, despite the fact that the formal parameter inside of the function has been modified. So that's a little bit of scoping, which is something that you guys will have to absorb at some point during this course. You know, with respect to getting concepts, it's always better sooner rather than later, but, you know, we're not quite to the point where scoping is like essential knowledge, but we will get there in probably about a week or two. Yes. Python uses a mechanism called pass-by assignment, which means that types would be changed. Sometimes they would not be. Anyway. It is recommended that you do not modify the function parameter. So, to explain why it's possible but not recommended, there are different meanings to assignment operations depending on what it is you're assigning. So, this is a thing that we will get into depth quite a lot when we talk about elementary data structures. But when you use assignment on data structures in Python, that's not actually, like if you, for example, let's say you had a list L, 1, 2, 3, and you assigned H is equal to L. You're not actually duplicating L. H becomes a reference to the same memory that L is pointing to. So if we modify L, the same change shows up in H. You don't have to understand this just yet. The important point to understand is that assignment sometimes behaves in a way you wouldn't expect, so it's not good to rely on it working. So that's why it's good to assign. It's not necessarily a good thing to always modify your function parameter. But, that's kind of a stylistic point. Let's just see if we've lost everybody yet. Passing by reference. Python does not pass by reference, although it passes by assignment. Sometimes assignment is the creation of a reference, so in that sense it's passing by reference, but generally speaking, if you have two varieties. You have pass by value and pass by reference. Languages like C and Python and Java use pass by value, which means that the actual value of the actual parameter is passed into the function. Whereas languages like Visual Basic and a few others that I forget, Fortran, I think, uses pass by reference, which means that if you modify the passed parameter, then the parameter will be modified outside of the function as well. So, there you go. You miss being happy? Welcome to adulthood. Jeez. So, let's talk. There are a few common constructs that you should get to know with respect to loops. I've said before that, one of the goals of this course is for you guys to have the tools in your toolbox to be able to come up with your own solutions to problems. So these are not syntax, right? These are common types of constructions. It's useful to study them because, they're common, and it's entirely possible that many of your assignment problems could be solved easily using these mechanisms. However, they're always like, think of them as tools in your toolboxes, not like you have to solve a problem in this manner, right? There's no hard and fast rules for how to solve anything. It's real. I want you guys to absorb the idea of programming as applying tools to problems rather than applying fixed classes of solutions to fixed classes of problems. But anyway, so the two types of things we're talking about are counter variables and accumulator variables. So when you have a counter, that's basically what. Whoop! Oh my goodness! There we go. That's what I is in factorial 2 or 3. This guy is being counted. He's incrementing. A counter starts at a particular value, goes up to some certain value, usually as designated by the loop condition, and the counter variable allows the loop to be executed, some number of times. This is a very common construction for loops. It's like, well, I would like the loop to execute 50 times. You would have a variable that counts up to 50, and when it hits 50, the loop ends, and that's the purpose of the counter. The other is the quote-unquote accumulator variable. I'm probably jumping ahead of the slide. This is probably on the next slide, but f is the accumulator variable in this case because it is a variable that is being updated on each execution of the loop in order to it will eventually become the answer, right? But you are modifying it continuously in order to achieve the answer. So it's accumulating the correct the data that is going to be in the answer. So that's why it's called the accumulator. So with respect to a counting variable, you can count up, you can count down, you can count by twos, you can do all kinds of things. But generally speaking, the idea is you have an upper bound and a lower bound, and you are tracing through that range of numbers using the counting variable. The accumulator should be initialized to a value that's correct if the loop isn't executed at all. So a good example of that, if we take a look at n here, we know that the factorial of 0 is 1. That's a thing that mathematicians have decided for, We don't have to understand why mathematicians think that the factorial of 0 is 1. We just have to implement it, We're, generally speaking, we should defer to the mathematical expertise of mathematicians. Am I centered in frame? Yeah, I'm centered in frame. Good. So, with respect to if we get a 0 here, this condition is going to come out false the first time we try to execute it, right? N will be 0. 0 is not greater than or equal to 1. It is less than 1. Therefore, none of this code will execute. Therefore, you want to put something in your accumulator variable that is correct if none of this executes, which is true in this case, because the factorial of 0 is 1. So, here is a question. What does this code output? I'll give you guys a few, about a minute to enter your answers into the chat. So we've got def sum t, t being a tuple. I is 0, sum is 0, s is 0. while I is less than the length of t, s plus equals t at I. Return s. T is 5, 10, 15. We are looking for printing the sum of t. What do we get? So, we got a couple of people who think 30, and a couple of people who say D, and one person who has given us the reason that it is D, which is correct. So, this is an important thing to go over, though. The answer is that this program does not output anything. And those of you who entered C, you might be like, well, okay, but why wouldn't it output an error? If this is an infinite loop, isn't that an error? We consider it to be an error when our code doesn't give us what we want, right? So this is obviously a program that's trying to sum all of the elements of a tuple. If it doesn't output the answer, we consider that to be an error, but that is different. That is different from the code creating an error. An error is a code event. Like, when we say the code outputs an error, what we really mean to say is the code raises an exception. Exceptions are something that we're going to talk about, I think, in topic 6. But, yeah, I think topic 6. But this code would not raise an exception. When your code is stuck in an infinite loop, it's kind of similar to that one problem that actually, it's exactly similar to that one problem that your classmate was having with respect to star in brackets on Jupyter. Star in brackets on Jupyter means this code is currently executing. It's not outputting anything, right? It's not creating any errors, but it is definitely going wrong. So it would not output an error. What it would do is nothing. Because it's not outputting anything, however, this would be running forever. Basically, the program would stall. It would hang. It would look like it has crashed. Very often, when you have a program that just, on Windows where like the program, it goes gray and it says this program is not responding, and it's not like a typical one for, like, it sometimes does that when a game is loading, but this is not a game loading. This is just like, I don't know, some poorly written program, and it's just hung like that. Normally, something like that is the result of an infinite loop. So infinite loops are bad. They don't output anything, but they also don't create errors. That's part of why they're so bad, because the computer is not actually able to tell that this is a problem. So there you go. That's the answer is D. So when you have an infinite loop in Jupyter, typically this is caused by us forgetting to increment the counter. So in this particular case, the reason this is an infinite loop is because there's no statement here modifying I. So the assumption here is that I is being increased from 0 to the length of t. However, there's no I equals I plus 1. So that's what's causing the infinite loop. If you get one on Jupyter, if you go to kernel interrupt, that will stop it. Another way, if it's if it's a sufficiently bad problem, you can also go to Control Panel, Stop My Server, and then restart the server. You'll lose any unsaved changes that way, but that's like the hard reset. If you're doing things in the command line and you hit an infinite loop, all you need to do is hit Control C. So Python 3, while true, pass. Oop. This is the, there you go. See how it's not bringing the prompt back up? If I hit Control C, that's a keyboard interrupt. It works in Bash as well as the Python prompt, but that will terminate the process that's currently executing. Control C. That's an important key combination to know. So, and while we're at it, and now for something completely different. Let's talk about typecasting. So, typecasting is the way that programmers refer to converting between different types. Python sometimes does this implicitly. That is to say, without having to do anything. Without you having to do anything. So if you add an integer to a floating point number, you get a floating point number back. That's, what's going on is 2 is being typecast as a float, and then the floating point operation is being performed. You can also explicitly convert from one type to another using these type conversion functions, int, float, string, etc. So, if we take that and we then wish to interpret it as a float, or as its integer, notice that it just drops the decimal place rather than rounding it. There you go. But yeah, you can also convert to strings. There you go. And an interesting one that we'll get to. It is also possible to convert between different types of data structures this way. In particular, if you have a tuple, let's say, and you want it to be a list, you can convert it that way. Notice it's using square braces now. Lists aren't a thing we've talked about yet, but we'll talk about them quite soon, believe me. So you can actually convert between stuff that way, which is kind of cool. Notice the string interpretation of the tuple is essentially what you get if you ask the interpreter to print it for you. Just enclosed in quotes. There you go. I'm going to check for questions. Yeah, it shouldn't have put anything. How do you format decimals to a certain number of decimal points? You have to use the format tag, as discussed in a previous slide. There's a whole slide on that, and I will leave you to take a look at that. Yes. So, for all the test cases on the assignment, if you're getting true for the test case, then you have got it correct. And if it's an assertion, there should be no response. That's also correct. How would int nope work? Good question. Int. So the question in more general terms is, what does Python do if you try to convert to an integer something that is very strictly not an integer? And the answer is, it raises an exception. You get an exception called a value error. So, invalid literal for int. However, if you have a string that is a number, it is fine converting that. It has to be composed of numerical characters. Yeah, we have a test coming up at the end of week 4, which will be next Saturday. Don't worry, it's not designed to crush you guys, crush your spirits. However, it is a test, so studying would be good. So let's talk about if statements. We've talked about them a little bit already, and you've seen some examples. These are the flowchart interpretations of if and else statements that we've seen so far. However, we're going to introduce a new type, which is the Elif. So, if you wish, sometimes what you want to do is you want to chain together multiple conditions. So, an example would be if, let's say we have some value x, right? Some x is equal to 19. If x is less than 0, print too low. Elif x is less than 10, print just right. Else print too high. There we go. So there's an implicit order that's going on with these. The first condition that's tested is B. If B is true, then S executes, and none of the rest of this executes. If B is false, then it checks condition C. If condition C is true, then it executes T. Otherwise, it executes the other branch, in this case, U. You can actually chain together as many conditions as you like using Elif. Elif is an abbreviation of else if, which is how other programs perform this type of operation. So you can have like 50 Elif cases that are going on inside of your program. Doesn't matter how many. Can you end with elif instead of else for the third example? Yeah, you don't have to include else. Just like you don't have to include else here, you don't have to include it there either. Yeah, that's correct. And the way that you would interpret that in terms of this diagram is you would just remove the U block here, and it would just be a straight pass-through. There's not much difference between this and nested if statements as well. But anyway, so let's talk about an example. Write a function that determines whether a number is even or odd. Here we go. So we have a function, EvenOdd, takes parameter n. If n modulo 2 is equal to 0, then it's even. Otherwise, it is odd. So, just a quick recap on modulus. This is remainder of integer division, right? So if we have some value 19 mod 2, the value is 1. That's because 2 divides into 19 9 times with one remainder. 1 is the one remainder. If it is 20, 2 divides into 20 10 times with no remainder. You can do some interesting things with this, like isolate the last digit of something, isolate the last 3 digits of a number. You can, if you couple this with integer division, you can extract a particular place value out of a number using modulus. It's kind of cool. But anyway, it's also very good at telling us if a number is even or odd using mod 2. Questions? Sure. So, let's think about the question of divisibility. Write a function that determines whether a number is divisible by 2, 5, or 10. Question: what does this program output? Def divisibility n. If n mod 2 is 0, return by 2. elif n mod 5 is 0, return by 5. Elif n mod 10 is equal to 0, return by 10. Print divisibility 5, comma, divisibility 10. This slash just indicates that we continue on the next line. So, what do you guys think is going to be the output here? Please enter your answers in the chat now. Yes, it outputs a string. That's funny. Maybe that's applied to something completely unrelated. So, the general consensus seems to be by 5 by 2. So, divisibility 5. For 5, 5 will fail this condition because 5 mod 2 is 1. 5 mod 5 is 0, though, so it would return by 5. With respect to 10, 10 mod 2 is 0, so it would, in fact, hit this case. Good job, everybody. Oh, yeah, okay. Well, anyway. So, what if we modify the function in the following manner? Notice that we've swapped the mod 10 and the mod 2. What we would get as a result, then, is, well, what do you guys think? Answer in chat. What would the result of this program be? By 5 by 10. We have a couple of people who answer. Some person thinks no change, but everybody seems to be on the consensus that it's by 5 by 10. So, for 5, you fail this condition, but you pass this one. 5 mod 10 is 5. 5 mod 5 is 0, so that would be the first one. The second one, divisibility 10. 10 mod 10 is 0. So the second part of the string would be by 10. Good job, everybody. How about this one? We now have some nested if statements. So, if n mod 2 is 0, then if mod 10 is 0, but return by 10, else by 2. And if elif n mod 5 is equal to 0 by 5. So, if our divisibility, our output here, what would it be? What do you guys think? People think by 5 by 10. Yes, that would be true. So, in this case, with divisibility by 10, this case would come out true. So, we then test this one, which would also come out by true, so we would get by 10. And of course, the first one would be by 5 again. There we go. And here's another alternative to that. Rather than testing mod 10, because 2 and 5 are both factors of 10 simultaneously, this would be another way to do that. Cool. So, hopefully that's reasonably straightforward. So, So let's talk about something that happened a few years ago, which is a brief foray into the interesting and complex world of computer security. So, a few years ago, there was a vulnerability in most Intel and AMD CPUs that caused a lot of problems for a lot of people. And the problem with a bug in your processor itself is that if the bug is in hardware, you can't really patch it out with software. Well, okay. Jeez. Oh my goodness. Anyway, so we're gonna go through how this bug existed, because it's kind of interesting. What? Come here, you. Oh, you're gonna make me chase you, are you? Well, fine. I won't. I'm not gonna chase you. So, there were 3 conditions that had to conspire simultaneously to create this vulnerability. And if you know anything about the processor market, between Intel and AMD, they basically have the entire market share between them. At least with respect to computers. There you are. Boom! Look, there we go. We're going to talk about stuff. Okay. Whoop. 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 Ow. Ow. You. Stop that. There we go. So, the first ingredient in Spectre was branch prediction in if statements. So, modern CPUs often have multiple cores. One of the advantages of having multiple cores is that you can perform multiple operations simultaneously. Believe it or not, before the existence of multiple core CPUs, a CPU could only do one operation at a time. So, one of the things that these new CPUs do is they can predict they will attempt to make a prediction about an if statement, which way it's going to go, and compute the results of that branch of the if statement in advance of the sort of normal program execution reaching it. If that is a correct prediction, then you've saved a certain amount of time. If it's not, then, worst case scenario, you just have to go through the program as usual. So, this is particularly useful when you're doing calculations that are kind of dull but still computationally expensive, like square root. So, branch prediction on if statements. That's ingredient number 1. The way that it manages this is if the branch prediction was wrong, the CPU resets all of the variables and runs the other branch and continues it as normal. Just to remind you of our von Neumann architecture, the CPU has both a control unit and an arithmetic logic unit, both of which are communicating with the memory. One particular thing about memory, though, is modern computers, and modern is defined as computers that have existed for the last 15 or 20 years. Modern computers have a memory hierarchy of caches, which improve in performance. So what cache memory is, that's C-A-C-H-E, cache memory. Cache memory is used to accelerate the process of loading and unloading data. In terms of electronics engineering, you have a trade-off between the speed with which data can be accessed and the permanence of that data. So there are certain types of memory that are very, very fast, but that memory degrades relatively quickly and needs to be refreshed in order to, basically, like, you have bit decomposition that occurs at a relatively high rate in very, very fast forms of memory. But if you're using the memory fast enough, it doesn't matter if you only need the memory for some fraction of a millisecond, and it takes, like, after 5 minutes, the memory will be completely, unusable. The data in the memory will be completely unusable because of data decomposition. It doesn't really matter. That's still a good solution. It speeds up the process. Whereas something like the hard drive is very slow to access, but the values that are stored on a magnetic hard drive, will stay stable for, decades. So, anyway, looks like we're out of time for today. We'll resume talking about Spectre next time. I guess that's next week. But, yeah, cache hierarchy. I will now take your questions. You missed one lecture and now you are confusion. Well, it's a good thing they're all on YouTube then. You can just go watch the one you missed. Cat equal true. Yes. When she comes up to me and shouts at me, she has to go on stream, whether or not, she wants to. Anyway, yeah, so that's good. Yeah. Yeah, I'm not a huge fan of pre-recorded lectures, because then I don't get to, simulate class participation. Like, to me, class participation is really super important. Can I teach you 1JC3? I don't know. Who's teaching 1JC3? I wouldn't want to step on any toes. I'll teach you anything as long as the department's willing to pay me for it. What is the use of f equals 1? I don't know what you mean. In what slide? Oh, it's the accumulator variable. That's where the factorial that will eventually be the output is stored. So, yeah. Cool. All right. Yeah, I guess we're kind of getting into the phase of the semester where the initial enthusiasm for being in school has at this point almost completely worn off. The grind of it has set in, and the fact that that grind is made worse because there's very little human interaction in a direct manner. Oh, Dr. Farmer's a good prof. I like Dr. Farmer. But yeah. Are we getting tested on the reading material at all, or is it purely optional? It is purely optional. You will be tested on your ability to write algorithms. Yeah. Yeah, Curtis. Let's move to Zoom. No. In Zoom, Zoom is terrible, and they want money for it, so no. If we were going to do anything, we'd do MS Teams, but no. Have we gone through all the material for Assignment 1? Yes. Assignment 1 is based on Topic 2. There you go. Will I be having any CS courses down the line? Who knows? We'll see. The test format is Jupyter. Is there a computer science help center like the math help center? Technically speaking, yes. The person that you'll want to hit up for that is John McNamara. He's, sorry, Nakamura. I'm getting names confused. Yeah. So, yeah. He's sort of designated as the CompSci Help Center person. I'm not sure how things are working this semester, but it wouldn't hurt to email him. The tests and exams are going to be precisely similar to the assignments. Yes. Yeah. I